our channel Edu9, and today we are going to discuss about symmetric group of order n. Let S be the set of all permutations on the set 1 to n. Because we are asked to discuss about the symmetric group of order n, and symmetric group is mainly formed on the basis of permutation mappings. So first of all, we consider a finite set with n number of elements, and the elements are 1 to n, and we make a collection of all permutations on the set 1 to n, and we name the set of all permutations as S, and we know that all the permutations mappings are bijective mappings. So first of all, we have to prove that the permutation mappings, that is the collection of all permutations mappings on the set 1 to n is closed under the binary composition stated here, that is multiplication of permutations. So we consider two elements f and g in S, that is f and g are two permutation mappings. Clearly then f dot g belongs to S, because we know that multiplication of permutation mappings of same order must reply us another permutation mapping of same order. So f dot g belongs to S, and this result must hold for all fg belongs to S. So we can say that S is closed under permutation multiplication. This is the closure property holds. Now our target is to establish the associativity. So we all know that permutation mapping is a bijective mapping. So bijective means injective plus surjective, and compositions of mappings, we know that compositions of mappings is always associative. So combining these two relations, we must have multiplication of permutation is also associative. So the associativity property also holds in the set S, which is the collection of all permutation mappings on the set 1 to n. And right now we have to establish the identity element property. Clearly the identity permutation on the set 1 to n will be the identity element of S. What is the identity permutation on it? Identity permutation is this, and it will satisfy the result I dot f equal to f dot I equal to f, where f is any element between the S, that is f is the any permutation on the set 1 to n. This is the identity element property. Now we have to establish the inverse element property. We all know that the permutation mappings are mainly bijective mappings, and we all know that the mapping which are bijective must be invertible. So the permutation mapping also be invertible, and if this 1 to n, f1, f2, fn, this is the general format of a permutation mapping, is a given element in the set S, then the inverse, that is f inverse, will be f1, f2 fn, and 1 to n is the inverse of f in the set S, as f dot g equal to g dot f will reply the identity permutation. So in this way we can find out inverse for each element belongs to S. So inverse element property is satisfied. Now our question is, we have already established the four properties, the four required criteria for a group, that is closure, associativity, identity, and inverse. Now we are asking a question that is the group S is a commutative group. So we have to think about the commutativity. Here multiplication is not commutative. Why? We consider two elements, f1 to a 2 cycle and g equal to 1 3, this is a 2 cycle also. But multiplication of f and g, that is multiplication of these two cycles will provide us a 3 cycle as 1 3 2, but the multiplication GF which returns us 1 2 3, which is also a 3 cycle, but the values of these two multiplications are not same. Therefore F dot G is not equal to G dot F. Hence the commutativity of this set does not hold. So we can say that the collection of all permutation mappings forms a non-commutative group. So S is a non-commutative group with respect to permutation multiplication, and we denote it by Sn, where n is a natural number. Now we are going to discuss Klein's 4 group. What is Klein's 4 group? We have the binary composition defined as above, where S is a set of 4 elements, that is E, A, B, C, and the properties of those elements are given as E naught A equal to A naught E equal to A, and so on. So during this time we see that S is a finite set and naught is a binary composition. We are given that. So we are going to composition table. This is our composition table. We can see that E naught E equal to E. It is defined already. E naught E equal to E. Again E naught A equal to A. This is also defined. Similarly E naught B equal to B. E naught C equal to C. Again A naught E equal to A. This is also defined already. A naught A equal to E given. A naught B equal to C, it's also given. A naught C equal to B, it's also given. Now B naught E equal to B. B naught equal to B. Now B naught A equal to C. B naught A equal to C. And B naught C equal to A. This is also given results. And now with the composition of C, C naught E equal to C. This is given relation. C naught A equal to B. C naught A equal to B, and C naught B equal to A. C naught C equal to E. This is our composition table, and from the table we can see that the closure property holds because all the composed elements are in the set S, so closure property holds, and associativity holds due to the definition of the binary composition, and identity element strictly is E, E being the identity element of the set set S due to the definition of the element E. And for inverse element we can say that each element is self-inverse as E naught E equal to E, A naught A equal to E, B naught B equal to E, and C naught C equal to E. From the definition of inverse element we can say that each of the elements of the sets are self-inversed. Also the composition table is symmetric about the principal diagonal. We can see that AA, CC, AA, B, so this portion is a image of this portion. So from this it is clear that the composition table is symmetric about the principal diagonal. Hence this is a commutative group of order 4, and this group is known as Klein's 4 group, and this is denoted by V4.